Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
System for high-performance virtualized routers.
Good morning. So this talk is about ShaRE, the Shangri-La runtime environment for high-performance virtualized routers. So you know what routers are. I'm going to tell you today what virtualized routers are, why we need high-performance virtualized routers, and how a runtime system will enable us to build such high-performance virtualized routers easily. Internet today, as you know, has grown to be much larger than what it started off. It started off as a simple network of 25 nodes. And the initial users of the internet were technical, mutually trusted, and not so demanding. And were running simple applications like Telnet, FTP, and email. And today, if you see, the internet itself is a network of thousands of networks with millions of nodes connected. And the users are also inexperienced and at times malicious and demand good performance from the internet. And the applications that we are running also have become substantially complex, like search, e-commerce, streaming video, games, etc. Despite the change in the needs from the internet, the architecture on which the internet is based hasn't evolved. It still provides the same best effort service. There is still no accountability of who sends what into the network. And the IP address space, which can uniquely identify nodes on the internet, is restricted. And this has been a known problem for more than a decade now, and people have been building better protocols and architectures in order to fix the problems, in order to address the new requirements. However, the internet hasn't changed much. The reason is the internet has become so large in its size and scope that it becomes risky to modify anything, and that's why people are scared to put any modifications. And there are many organizations that own parts of the internet, and it becomes hard to reach consensus on what should be changed in the internet. This phenomenon is being termed as internet ossification in the research community. And recently, there has been a trend towards addressing this ossification using overlay networks. The idea of overlay networks is to use a set of PCs connected to the internet and deploy services as overlays on top of these PCs. Clients can now connect to one of these PCs and get that particular overlay service. There have been several such PC-based substrates built both in the research front and the commercial front. On the research front, we have Planet Lab, and on the commercial front, we have Akamai. These PC-based substrates provide us the flexibility to host any kind of richer services. They work on the existing internet, and they're incrementally deployable. You can deploy services incrementally. And these benefits of the overlay networks have enabled us to build richer and richer services in the recent past. We have content distribution networks, we have better quality of service, overlay services, and better routing facilities. Now, if you look at these nodes that are forming the building blocks of such substrates, these are the nodes that I'm calling virtualized routers. They are hosting multiple services, and they are forming routers between the clients and the particular service that we are providing to the clients. Currently, these virtualized routers are PCs, and they're good for small deployments. In order for supporting real user traffic and really address this internet ossification problem, we need high-performance virtualized routers as opposed to just PCs. This is because the number of services that we are supporting is increasing. The popularity of the services are also increasing, which means more and more packets have to be processed per second. And the complexity of services is also increasing. That means the amount of time you're spending to process on each packet is increasing. A design trend towards getting high performance out of this system is to exploit inherent parallelism in the domain, in the packet processing domain. You can process multiple packets simultaneously. There is no dependence across many packets. You can do this by using clusters of PCs or SMB-based systems. However, the industry is going more towards building these multi-core, multi-threaded processors. They are programmable and provide flexibility to host any kind of service. And they'll provide performance by allowing you to process packets in parallel. An example of such a processor is the Intel's IXP 2800 network processor. This contains 16 processing cores, each processing core containing 8 hardware threads, and which in itself makes it a 128-way parallel system. You're processing 128 packets in parallel. Further, on chip itself, there are several hardware mechanisms that are put in, like message passing mechanisms, shared memory communication mechanisms, and fixed function accelerators like hash units and crypto units in order to speed up packet processing. More generally, there is a trend towards building such multi-core processors even in the general purpose domain and the graphics domain. The idea is the same. Try to exploit the parallelism in order to support higher throughput applications. IBM is building a cell processor which is tuned for the graphics domain, and the architecture looks very similar to this architecture. Yes?
So these were originally video controllers.
Sorry?
The IXP chip without the video controller was ported over to be a network processor.
Okay. Nice. Yeah. So the problem with using this kind of a hardware is managing the complexity of the hardware itself. There are very few good tools to program such hardware currently, and the available tools expose the hardware details to the programmer to make the best use of the hardware. However, if you think about real systems, they're going to contain multiple such processors, and along with them are going to contain general purpose processors, several fixed function coprocessors, etc. So if we expose the hardware details of all such processors to the user, it becomes hard to the programmer. It becomes hard for the programmer to write programs onto this hardware. And as a result, it becomes time consuming. And the code that we end up writing is also non-portable because the combination of hardware that we are picking is going to change. Further, since network traffic fluctuates with time, the resource allocation that you will do when you're programming such systems will be inefficient with time, and the system will become less robust to such traffic fluctuations. In this direction, we have started a project at UT Austin called Shangri-La in collaboration with Intel Research and Development at Portland. The goal of this project is to make this class of multi-core systems as easily programmable as today's workstations or clusters. This programming environment has two goals. First is that it simplifies the programming and yet efficiently utilizes the features to achieve high throughput out of these hardware. And secondly, it makes the system robust to traffic fluctuations. We believe that if we have such a programming environment for such multi-core hardware, then we can enable rapid deployment of high-performance virtualized routers, which will enable us to address the internet ossification effectively. So the programming environment, just like any programming environment, contains a high-level language, a compiler suite, and the Shangri-La runtime environment. For completeness sake, I'm going to talk a little bit about the high-level language and the compiler suite, but the bulk of the talk will focus on the Shangri-La runtime environment, which is my dissertation thesis. Let's look at the language and the compiler. The Shangri-La programming environment contains a language called Baker. Baker uses a streaming style of programming, where programs are written as graphs of packet processing functions that communicate packets using queues. And this kind of programming style has been used by several systems in the past. SADA uses it, Click uses it, Synthesis kernel used it. What I want you to just appreciate here is this code snippet from a particular Baker packet processing function. A packet processing function is a set of well-defined operations on a particular packet. What this packet processing function is doing is, on a packet, it looks at the MAC address, and then depending on what the MAC address is, it classifies it as whether it should be routed or it should be bridged. Now, what I want you to appreciate here is that the syntax is simple to write, to understand and write. It just looks like C or C++, and it does not expose any hardware details to the program. It does not contain anything related to what hardware we are going to program on. Okay. After these programs are written, a pipeline compiler creates aggregates, larger sized aggregates, which can be loaded onto the hardware. And there are several ways you can aggregate these packet processing functions. You can create a single aggregate out of all these packet processing functions and load each aggregate, load this aggregate on multiple processing cores you have on the network processor, or you can create multiple pipelines of aggregates and load only each aggregate onto one processor and communicate across processors using some message passing communication. Which alternative to choose depends on several considerations. You need to make sure that these aggregates fit in the instruction cache of the processing core, because these aggregates behave as loops of code. Once a packet is dequeued, you do some processing, send out the packet, and do the same processing for the next packet you dequeue. In order for the performance to not suffer, the whole loop has to fit in the instruction cache. And that's why you need to make sure that these aggregates are small enough to fit in the instruction caches of processors. Secondly, you need to make sure that the communication between these pipelines of aggregates is minimized, because you don't want to contend on shared resources. And that's why the size of the aggregate depends on how much how much data sharing you can reduce. These are all the considerations that PyCompiler takes care of and creates these aggregates, which can be used by the runtime system. Okay, so just now let's come to the Angular runtime environment. The runtime environment, just like any other operating system, does two main functions. It is abstracting out the resources, hardware resource details, and automates the resource allocation. And it does adaptation or resource management in order to provide robustness to traffic fluctuations. So let's look at how it does each of these in detail now. Okay, what really is happening in the resource abstraction is, pictorially, we are writing Baker programs for this kind of hardware. So the ShaRE, the Angular runtime environment, contains a packet processing oriented resource abstraction layer, which abstracts out the resources. That's the API we are programming to. Now, once these aggregates are formed, the aggregates contain the abstract interfaces to which we coded. So those have to be resolved before we can map these aggregates onto the hardware. And that's what happens using the mapping mechanism. So let's go into a little detail about the PRAL and the mapping mechanisms. PRAL provides domain-oriented abstractions. The idea is that we know that packet processing is pipelined. So for packet processing functions to communicate packets with each other, we need an abstract interface for putting in packets, which is a communication channel, onto which you can enqueue packets, dequeue packets, and you can do other operations like finding out the length of the packets, etc. How exactly that communication channel gets implemented is dependent on dependent on the hardware. Second consideration is, we know that the underlying system is parallel. So if packet processing functions are using some shared state, there has to be some way of synchronization. And so the resource abstraction layer provides a lock interface so that the packet processing functions can acquire that lock before they do on some shared state before they use the state. And finally, whatever fixed function accelerators are there, all you need to know is how to evaluate that using that interface. For example, if I have a hash, I just need to know that if I'm given input, if I give an input, the system returns me the hash value. It doesn't depend on what hardware is present in order to make that. You can implement it in hardware, you can implement it in software. So that's what the resource abstraction layer does. Once these aggregates are formed after compilation, we have to resolve the references of these abstract interfaces onto the hardware. In order to understand that, let's take this example. The goal of this mapping phase is to maximize the use of local resources in the hardware in order to maximize the throughput. For the different resource abstractions that we are having, we need to use the local as local resources as possible. For example, logs, you want to put it in local memory, or channels, you want to use the fast message passing communication. So this is a simple example of a set of aggregates communicating as follows. A does classification on packets and sends it to B or D. Now, B is dequeuing a packet from its abstract channel acquiring some lock on the some shared state, does some processing on the packet, releases the lock, and then enqueues the packet. Similarly, the other aggregate is also doing the same. So now let's say this is the simplified hardware we have, and there are 4 processing cores in the system on the hardware. Each processing core has some local memory, and each processing core can communicate with its next neighbor using a next neighbor channel. This is the message passing communication channel, which is the fastest implementation for communication packets. These processors can also communicate using the global shared memory, but that will be a little slower than this one. Now, let's say the processing requirements of the aggregates are such that A needs 1 processing core, B needs 1, and D needs 2 processing cores. How would we map onto this hardware such that we maximize the use of local resources? Okay. Since we know that A and B are communicating, are sitting on only 1 processor, are going to sit on only 1 processor each, and they're communicating using a channel, if we map them onto adjacent processors, then I can use a next neighbor channel in order to communicate. I can't do the same thing for A and D because D will be on 2 processors. A cannot communicate with D using next neighbor channel on 2 processors. Similarly, the locks. Since B is running on only 1 processor, I can use a local lock, but since D is running on 2 processors, I have to use a global lock. So that's what happens in the mapping phase. You're choosing the right implementation on the hardware in order to implement the particular interface.
So when you say D is running on 2 processors, you don't mean that you split, like the call graph is split across 2 processors. You mean that D just has enough work to do that you want to run 2 copies. So that's why you can't just send. It's not like you can send the information to P3 and then let P3 propagate it before.
Right. Okay. So D is the same functionality. It's replicated.
Okay.
Processors. Yeah.
And then on the ISP, how many next neighbors does each processor have?
There is 1 next neighbor.
Just 1.
Yeah. So it's a set of registers basically.
Okay. So
You can communicate. You can keep sending packets using that next neighbor. Okay. Now, after mapping these aggregates, the system can run and start processing packets. But now what happens if the traffic fluctuates? You need to provide robustness to such traffic fluctuations. And that's the second functionality of the runtime environment. So what does traffic fluctuation really mean to us? Traffic fluctuation means that the processing requirement for a particular aggregate can change. It's possible that since initially D was requiring 2 processors, but the traffic has fluctuated such that B requires 2 processors now, instead of D requiring 2 processors, and D requires only 1 processor. How do we take care of such conditions? The idea is simple. Whatever aggregates are mapped onto the hardware, there is a scheduler that continuously monitors these aggregates and uses a set of mechanisms to remap the aggregates onto the hardware. So we are determining when the system should adapt and then how the system should adapt. We are going to details about each of them. When to adapt? This kind of runtime adaptation is not new. Conventional operating systems, server clusters, real-time systems have been doing for a long time now. So why not just use one of those conventional scheduling techniques here? The problem with using one of those techniques is that the packet processing domain provides some unique features or unique characteristics which make those solutions unusable. To understand what exactly happens, let's go into details about what the conventional techniques are and how they get affected by the unique characteristics. Now, these conventional techniques can be divided into quantum-based scheduling algorithms and observation-based scheduling algorithms. So you're either doing some amount of processing and then shifting, or you're continuously observing the system. A class of quantum-based scheduling algorithms are request-level scheduling algorithms. These kinds of algorithms are typically used in real-time operating systems, like earliest deadline first. After processing each packet or after processing each request, you determine which is the next request to in the earliest deadline in order to be processed. That has to be processed. Yes.
Actually, I have a basic question. So you are mapping these tasks onto processors, right?
Right.
What is the reason for doing that? This is to maintain the make sure that the processing code fits in the cache of each processor, or because you said earlier that each processor can support 8 threads or something.
Right.
why don't you say that there is a thread for A, B, C, and D running on each processor?
Currently, the reason we put threads on each of these cores is to mask off the memory latency. So each thread really is sharing the same instruction store. So all threads are executing the same code. That's why there is no code. You can make each thread execute a different kind of code, but there is no real incentive in order to do that. It just the
So
system.
you avoid the mapping problem, right?
Sorry?
You don't need to do the mapping of tasks to processors. You just, I guess what I'm trying to understand is why can't you have all 4 kinds of processing, A, B, C, and D, run on all processors?
Oh, that's because of the instruction cache.
So is that the reason? Okay.
Yeah, that's the reason. So you want to make sure that the whole loop that is going on each packet fits in the instruction store or the instruction cache that you have in the process. Okay. So the request level scheduling algorithms are the ones that after processing each packet, you're going to see which packet is the one which will miss its deadlines the next, and you switch to that aggregate and start processing that particular aggregate. Now, these kinds of systems can reallocate processors at request boundaries and can be substantially inefficient, especially because in this domain, the time you spend processing a packet is much smaller than the time you spend switching a processor. The packet processing time is in orders of microseconds, 10 microseconds. Whereas the context switch time is approximately 1 millisecond in order for a processor to start running a different aggregate. And as a result, you're wasting a lot of time context switching as opposed to processing packets. And remember that context switch actually reduces the processing capacity of the system. So fixed quantum scheduling algorithms fix this problem that the request level scheduling algorithms have. They amortize the context switch overhead by processing a lot of requests before you switch a processor, the context of a processor. The idea is to choose a large enough quantum which is much larger than the context switch time. However, in the packet processing domain, you need to make sure that the delays that the packets see are not much long, because if the packet goes through multiple hops, if it goes through 10 hops and at each hop you're adding 10 milliseconds, you're going to see 100 millisecond delay on the other side, which is unacceptable to clients. So what we want is that this delay bound that is there on packets is restricted. Yes.
But you're only going to add that delay when you actually have a context switch. And it's not likely that every router on the route is going to decide to make this switch decision right at the same time, right?
Right, but there can be packets which will see such bounds, such delay bounds. So we need to make sure that you're not
If they're very
getting
rare,
into this.
You see that all the time in beta queuing delay, right? So, I mean, it just seems like you could play a probabilistic game here, which is that it doesn't happen very often. You know, the internet is best effort, so who cares? But anyway,
Yeah, it's debatable. You can say that I can live with some packets seeing very large delays.
If
But
it's very rare, I guess.
Right.
Anyway.
So the delay tolerance that we can provide on packets, if I use a quantum-based scheduling technique, is much larger. It will be of the order of Q, which is much larger than the context switch time, which is already of the order of milliseconds. And so these kinds of algorithms become unusable. The observation-based scheduling algorithms are of 2 types. One type is prediction-based. You're measuring how the packet arrival is in previous intervals, and using those measurements in the current interval, you're determining what the allocation should be. And these kinds of algorithms are typically used in web servers. Over a period of time, you can measure what the arrival rate is and allocate according to the history. But the kind of timescales that we're talking about in the packet processing domain, which is fine timescales like milliseconds, it has been shown that predicting traffic at these timescales is hard, and at the same time, it's not accurate. And as a result, whatever we are doing based on history need not be what is required in this current interval. So it can either cause unnecessary context switches, or it can make a lot of packets missing their delay bounds. And finally, there are a set of observation-based scheduling algorithms which are reactive kind. They really see a packet missing its delay bound and then add processors. That's when they've detected that, okay, the resources are not sufficient for this aggregate, and that's why I have to add one more processor. However, in this domain, the inter-arrival time of packets can be much smaller. Even if I consider 1 Gbps rate, I'm getting packets 1 every 500 nanoseconds. Whereas the packet processing time is tens of microseconds. So after processing a packet, if I realize that I have to switch I have to add one more processor, I have already received a lot of packets because of the inter-arrival time. And at this time, I'm adding a processor, which is going to take 1 millisecond to come up and start processing. So that's going to be a lot longer. So these kinds of algorithms are not really agile. We need more agile algorithms than this. Okay. So the goal of a scheduler for this domain is to maximize the number of packets that gets processed within their delay tolerance and yet minimize the overhead of context switches. We use two principles in order to address these two goals. First is detect as early as possible when a packet is going to miss its delay bound. So ideally, you can monitor the aggregates queue, and whenever a packet enters, you see whether the packet has crossed the threshold. The queue length has crossed the threshold when I enqueue that packet. And if I can determine that threshold, then I can adapt based on the threshold. I can determine that there is more requirement of processing capacity. The second principle that we use is to explicitly minimize context switches, which is we'll reallocate a processor only when a different aggregate really requires it, which means only when a different aggregate touches the threshold, its threshold. Otherwise, even if a processor is idling for a particular aggregate, we will not switch it. Because if I start switching it, there is a large context switch time that I'm paying, and I don't want to pay that unless necessary. By the way, this queue that I'm talking about is really the channel that we're seeing here. This is the channel that we're monitoring. This is the queue that we are monitoring. Okay, so now based on these principles, let's see how to determine when processor should be allocated and when processor should be released for aggregates. Yes?
So how does the 1 millisecond context switch time come about?
There are two ways to address that. One is that you just minimize the context switch. You are aware that context switch time is large, and that's why.
I'm trying to understand why it is as large as 1 millisecond.
Oh, why is it as large as? The current hardware that we are dealing with has instruction stores, and as a result, you have to the programming, the writing into the instruction store, writing all the instructions into the instruction store takes that much amount of time. It's the hardware value that we currently have.
How large is the instruction store?
It's 4K instructions, and instruction store itself is on the processor on chip, but the code that you're trying to write onto the chip is on the SRAM off chip.
Is that loaded on demand, or is it preloaded before you start executing?
So in the mapping phase, when we were mapping, we are loading the code, and then we are starting to run the system. But when we are adapting, that's when we are writing the code again. You have to form the aggregates. When, let's say, one processor is changing from aggregate D to aggregate B, you have to rewrite the instruction store.
But you have to rewrite the instruction store completely. It's not like you can take a miss in the instruction cache and on demand fetch that from the SRAM.
Yeah, it's not that. Okay. That's why the whole amount of time it takes to write the instruction store comes in as the context switch time. Does that answer the question? Okay. So the first question is when to allocate processors to an aggregate. When to allocate depends on the delay bound that you're providing on packets, the delay tolerance that we can have as acceptable value, and the processing time per packet, and the number of processors that are allocated to the aggregate. These two in turn determine the rate at which the queue is being processed. Now, the idea of determining when to allocate is simple. You allocate more when the current J processors are not sufficient to process all the packets that are in the queue within their delay bound, the delay bound that we're placing. So the way I can calculate this is that in D units of time, one processor can process d by t packet number of packets. Which means if I have j processors, then I can process dj by t packets within d units of time. Right? Now, if I place a threshold on the queue and say that all these packets after the threshold and the packets that are there in the currently being processed in the processors have to meet their delay bounds, then these packets have to be processed within D, within the delay bound. So that means qlin j plus the number of packets here should be equal to this one. If it exceeds this, then that means that whatever packets I get will not meet their delay bounds. So that lets us determine the threshold that we are placing on the queue. It's all in terms of the delay bound, that the processing time per packet and the number of processors allocated. Okay, now let's see how we release processors from an aggregate. The idea is again simple, that when the queue is empty, just release some number of processors such that the rest of the processors are sufficient to handle the current arrival rate of traffic. Right, and you can calculate that easily. And this is where the second principle comes in. At this point, we are only marking those KJ processors as free. We are not really switching them to a different aggregate unless that different aggregate requires it. That different aggregate has to come up and say, okay, I need more processors. That's when we switch these free processors. Yes?
So how predictable is the processing time for a packet?
In the packet processing domain, the time to process a packet doesn't vary as much. So you can predict the value easily.
Yeah, but I mean, I thought your original sort of motivation was building overlay networks using hardware like this, correct?
Right.
An overlay network could be doing lots of things like.
But per aggregate, the amount of processing you are doing is defined. Each aggregate is behaving as a loop, right? An overlay application can be large. You're breaking that down into a set of aggregates, pipelines of aggregates, right? And each aggregate is doing a set of well-defined functions on a packet before it sends out a packet to the next aggregate, right? And a combination of these aggregates is forming that complete overlay service. Yeah.
So is it fair to say then that the aggregates are kind of like basic blocks? If you have a very complex program,
right,
then the rates, what you're measuring is, what you've done is converted the basic blocks have a reliable time it takes them to process a given packet, but now what you have is if packets come in and suddenly start using more complex behavior in the program and are now visiting more of these basic blocks, then what you have is effectively that thing you were talking about earlier where the arrival rate is hard to measure, it's hard to predict.
Right.
Okay.
And do you also end up having to not change the number of processors that are assigned to each aggregate, but move the processors around? So for example, previously you had that slide of one aggregate feeding two aggregates, and you decided to assign A and B next to each other, and then D was further away.
Right.
Now, if the load between A and D ends up increasing a lot, do you end up having to move D closer to A and move B away?
So I'll come to that in a couple of slides. In a few slides, I'll be coming to that exactly. So we have determined when to allocate and when to release for each aggregate. Now, what do we do across aggregates? We need to provide some kind of fairness and isolation across aggregates. Otherwise, an aggregate can have an unbounded requirement, thereby not giving any resources to the other aggregates. So we use a simple overload control policy here. When the cumulative requirement of the aggregates is less than or equal to the total number of processors, then there is no problem. We'll just allocate to the aggregates as required. However, if some of the aggregates are overloaded, then we first satisfy the minimum requirement that we're providing for the aggregates, which is the minimum of the current requirement and some guaranteed allocation that you're providing on these aggregates. And then we divide the remaining processors in proportion to the current requirement. A simple proportionate share allocation policy. Putting these three implementation details together, we first studied the behavior of the scheduler using simulation studies. We use a network service, IPv4 v6 gateway. This application forms an interface between an IPv4 world and an IPv4 v6 world and translates packets from v6 to v4 and v4 to v6. Additionally, it does some extra processing based on the kind of transport protocol that it is carrying. So that in itself gives us 6 aggregates if we just break it down into functional blocks. So we profiled an implementation of IPv4v6 gateway and found the packet processing times for packets at each of these 6 aggregates. Then we used edge traces from UNC Chapel Hill to run this simulation and used a context switch time of 2 milliseconds. And this is the exact value of the hardware programming that it takes on the XP2400. And I'm going to show you 2 experiments. The first experiment evaluates the design principles that we have chosen. And the second one shows the cumulative effects of putting this scheduler together in a system.
So what sort of things would the TCP aggregate be doing?
So when I'm changing the address that packet contains, the checksum changes.
Okay.
So I need to do some extra processing to recompute the checksum that I'm putting. Okay. So let's first evaluate the first design principle. We are trying to detect early, or as early as possible, when a packet will miss its delay bound by monitoring the queue. Let's compare it with the conservative Everest, which allocates processors when the first packet sees a delay which is much greater than, which is greater than the delay bound that we are providing. This is what represents these traditional reactive scheduling algorithms. You're waiting till a packet sees a delay bound before you're adding a processor. This graph on x-axis plots the delay tolerance, which is the parameter that determines the threshold in the Everest case, and determines when a processor is added in the conservative Everest case. On the y-axis, I have the percentage of packets that are missing their delay bounds. You can see that for various delay values, there is a substantial decrease in the percentage of packets that miss their delay bounds if I use early detection, which is what Everest is doing. And note that this is a log scale. So this says that the first principle that we are using is actually good. The second principle that we were using is to explicitly minimize context switches, which means we are reallocating processors only when a different aggregate actually requires it. Now, we compare it with an aggressive form of Everest, which is really doing work-conserving behavior, which means if there is some amount of work to be done in the system, I will never idle a processor. That's what the aggressive Everest does. So once a processor is released, it will greedily give it to an aggregate which currently has the longest queue, so that the average delay in the system is decreased. And this graph on x-axis again plots the delay tolerance, and on y-axis plots the average delay that the packets are seeing. So you can see that the aggressive form of Everest, instead of reducing the average delay, is actually increasing the average delay. And this is because every time I context switch, my processor is going to be unavailable for 1 millisecond, which is much larger than the packet processing time. Yeah.
In the first experiment, did you try doing C Everest where you trigger the reaction when they miss, I don't know, 80% of D or what? I mean, when they're getting close to missing D, it seems like waiting until you've reached.
Right. So the conservative Everest was actually an extreme, the other extreme.
What
right.
happens if you do something, where you allocate?
Yeah, we haven't done that. It's going to be between those lines. Basically, it's going to vary in between that because Everest is one extreme and the conservative Everest is the other extreme. It's just becoming the ends of the spectrum. Right.
I see. Well, one is looking at the outcomes and one is looking at the queue lines.
At the queue lines, yeah. We haven't. I don't have data. Okay, putting these 2 principles together, we compared Everest with several scheduling algorithms which we could have used. Quantum-based scheduler would have reallocated process after a quantum or when the queue becomes empty. Conservative Everest would allocate processors when packet delay exceeds the value D, and static allocation, which is currently used in these hardware, these kinds of hardwares, which is allocate proportional to some guaranteed allocation. And we found that for different amount of processing in the system, as I'm plotting again the percentage of packets missing their delay bounds, As the provisioning in the system increases, all the lines come down because you're having more amount of provisioning in the system. So you're able to meet more and more delays for packets. However, Everest substantially reduces overall the past algorithm. Yeah.
So can there be situations where context switches are cannot be avoided because you have so much processing to do that you take the number of processors multiplied by the instruction cache of each? That's not enough to fit all your processing code.
So you're considering a case where the whole application itself doesn't fit on the processor.
Yeah.
This system automatically takes care of that because every time the queue reaches a threshold, you're going to add a processor. But if you do not even have one processor to fit an aggregate, then that's a substantially under-provisioned system, right? Because the application itself is not fitting on the hardware.
I mean, it'll fit if you hit context switches, but I mean, what I'm trying to understand is
It will perform, but it will perform at a very low levels of performance. We haven't considered that case because I think we consider that it's an under-provisioned system. If the application itself doesn't fit on the processor. These kinds of processors will pay a lot of penalty because you are having to reload the whole instruction store before running anything. Yeah.
So I see there you're using d equals 2.1 milliseconds, which
Yeah.
is a very strange value. Is there?
There's a reason actually.
I'd love to hear it.
Yeah, I didn't get into those details because I would love to talk.
You can tell me about it later if you like.
Yeah, can I come back to that later? Yeah, that would be good. Okay. Sorry, you had a question?
I was wondering about the load of the external traffic. If that fluctuated, then you'd be flip-flopping back and forth in your provisioning, wouldn't you? Because one queue length would explode, you'd swap it over, then your traffic would change and you'd have to flip back. There must be some amount of fluctuation where your system is resilient to and some threshold where it's stuck in this flip-flop stage. Did you evaluate that?
So the frequency at which we are allocating just depends on how the queue is crossing that particular threshold. If you have a system which is, if the question is, can you construct a workload which will just make the system unstable by going just across that threshold that we are placing?
Yes, I think that in general, a lot of systems that just watch the queue length there, so that's the difficulty, is trying to make sure that your queue length is stable, or else introducing some kind of dampening factor where it's, it's over this limit for 10 seconds or whatever before you flip.
So that's where the second principle that we're using comes in. Unless there are enough number of aggregates, unless the system is overloaded, you'll never get into that condition. Because we are releasing processors, but we don't reallocate them. They're still processing the same aggregate. We just mark them as free, right? So if my requirement is 3.5 processors, but I have allocated 4, because of which the queue completely drained, I'll still not reallocate this 4th processor unless someone really needs it.
So that assumes your whole system is not maximized.
The whole system is not maximized. But the granularity at which you're able to switch processors is what is controlling how frequently you switch processors. Right. Yeah.
So do you have one aggregate that's dedicated to monitoring the queues from all the other aggregates?
No, actually these processors have a control processor, which is looking at all the slave processors. So that's where this scheduler algorithm runs. Okay. The Everest scheduler has now determined when a system needs to adapt. So there are new resource allocations that have to be remapped on the hardware. So now let's look at what mechanisms we need in order to adapt the system from one configuration to the new configuration. Let's look at this example again. Initially, these aggregates were taking one processor for B D was taking 2 processors. Now let's say the traffic fluctuated such that D needs 1 processor and B needs 2 processors. What happens on this hardware? So this resource remapping is not as simple as changing one D to B. This is where your question gets answered. Because A and B are communicating with a channel which is currently implemented on the next neighbor. We have to push it into the global memory so that B can communicate, A can communicate with B on 2 processors. And similarly, since D is working on only 1 processor, if I can move D to P2, then I can communicate using the next neighbor channel. Right. And the locks also. This lock has to be moved to the global memory, and this lock can go into the local memory. Yeah.
Where is the actual queue data in the case of A to B, where they're communicating on the neighbor channel? Where is all the packets? Where are all the packets that are in the queue? Are they sitting on this next neighbor channel?
When you're using the next neighbor channel, that's where the packets are.
That next neighbor channel actually stores a significant amount of data?
The next neighbor channel, actually, this is where the packet handles are, not the packets.
Okay.
The packets are still in the global memory.
Wow, and so
these are just registers which will allow...
The packet out of global memory doesn't swamp the savings you get from communicating on the next neighbor channel?
Sorry?
I mean, it seems like if A has to manipulate the packet out of global shared memory and B has to talk to global shared memory, that the little tiny savings you get from passing the handle across the next neighbor channel would be swamped by the fact that, okay, well, B found out about the packet right away, but now still had to go load it out of global shared memory.
Mm-hmm. So that's actually correct in this particular hardware. Okay. But there is no reason why we can't increase this register set to contain the whole packets.
But at that point, now you've got the trouble of when you do this reconfiguration, you now have to flush the junk out of that.
Move the packets, right? Either wait till the packets drain or move the packets to the higher global memory. Yeah. So all those overheads are the ones that get added to this context switch overhead, which is why it becomes larger and larger. So that's what happens here. In order to maximize using the local resources, we move these aggregates around and the channels around. And since we are moving, D was initially here and we moved D here, and the B also moved, and also the locks have moved from one implementation to a different implementation, and the channels moved from one implementation to a different implementation. All these can contain state. These aggregates can contain state in the local memory, which has to be moved, and the channels also have state and locks have state. So what happens to that state? We need one extra mechanism such that we can checkpoint and migrate that state so that the system does not is consistent. So the goal is to migrate all these states before you restart the system. Now there have been several process migration solutions for doing such things. You can consider an aggregate as a process and do exactly what the process migration systems do. However, we need to make sure that the overhead that we are incurring is minimum, because this overhead is going to contribute to the total context switch time. And that's what we need to reduce. So what we do here is to use this intuition about the networking domain. Each aggregate is behaving as a loop. So if I just wait till the beginning of the loop, then I still haven't dequeued a packet in order to process it. So I'm not having any stack state to migrate. And I'm not holding on any lock, because I'll hold on to a lock only when I start processing the packet. And so all we need to do is just migrate the channels, state in the channel.
Yeah. So, can you just repeat that again? The no stack state comes just because you think it's a loop, or because you do something with the compiler to guarantee that there's nothing on the stack? Like I'm providing a service like limited bandwidth to somebody, and I could easily see that have stack state in terms of counting packets that would traditionally be.
So that's not necessarily a stack state. That's a state that you're keeping as an application state, right?
Right, but I'm saying that depending on your compiler, that might be stack state, or it might not. So this is guaranteed by the compiler. That's not
this is guaranteed by the compiler. The compiler keeps only, it uses the local memory only for keeping the
stack. Okay, just wanted clarification. Thanks.
Okay. Putting these things together, we've built a prototype on the IXP 2400 network processor. Yeah.
Before you get into that, the switch that you showed before, you converted your two D processors into two D processors.
Right.
Excuse me, two Ds into a B and a B into a D. You could have instead just converted one D into one B, and that would have given you the amount of hardware that you wanted. But you're also talking about wanting to optimize some other things, like using local
resources.
And so forth.
Right.
Did you evaluate the trade-offs between the more? So in one case, you're doing more work with the hope of getting more benefit, but it may not be worth it, right? Maybe you'd be better off just doing a lesser amount of work because you're only going to go over there for a brief period of time and then go back, for example.
So these things are hardware dependent, and it depends on the. So the answer is twofold: whether we have done it here, or whether it's fundamental, right? Is it required?
Okay.
Right. We did it here, and we found that if we use local resources, it is going to give some benefit. But this benefit really is not substantial that you cannot use the global resources. But fundamentally, if you think these local resources are being put in order to make sure that there is minimum amount of use of the global resource, contention for the global resources. If I end up making these next neighbor channels to contain the whole packets instead of just packet handles, I'm going to see a lot more reduction in the traffic on the global memory. And most of the global memory actually goes off chip, which is much more costly than doing everything on chip.
Let me try this a different way. You've got, so you have to do a reallocation here because you need to have enough hardware in order to process the current load. And you've got more Bs now than Ds, so you need to turn a D into a B. That's one decision that you made as to how much hardware do I dedicate to each task. Another decision you make is once I've chosen how much hardware to dedicate to each task, how efficiently do I want to use that hardware? Do I want to use local resources always whenever they're available, or might I not want to do that because it's a more expensive context switch if I do that? You have made a fixed decision about the second one of those. I'm always going to switch as much as possible, always use as much
local
hardware as
resource.
possible.
Right. So
my question is, number one, is that really always a reasonable thing to do? And number two, did you evaluate at all the trade-off?
So which one to choose really is a policy decision, right? Ideally, we would want to have the flexibility in the runtime system to choose whether to use local resources or whether I'm better off using global resources. In our measurements, we found that there is a contention for the global memory, and you can construct.
So in other words, you actually tried it both ways. You tried where you do the switch from one B to a D to a B without actually doing the full local to global.
Right. So using global resources here is very simple. You don't do anything, right? In terms of adaptation, that resource remapping will not happen because it's just a matter of putting an aggregate onto a different processor and everything works fine because all resources are in global, right? As opposed to doing this extra step that you're explicitly moving the code or patching the code in order to use the local resources. So we did that extra step also as a mechanism inside the runtime system. If it's a policy decision to choose whether you want to use global resources only or whether you want to go to local resources.
Okay.
So putting these things, this implementation on a prototype IXP 2400, we evaluated both the two goals that we had for the runtime system. First is that we wanted to simplify programming by using this resource abstraction layer and automating the resource allocation. We could very easily build several applications using Baker and the resource abstraction layer provided by ShaRE. We could build a port scan detector, which detects port scanning attacks, which are typically used for spreading worms, and a worm signature matcher, which scans packets for some given set of signatures using some string matching algorithm. And a TCP SYN flood detector detects denial of service attacks. And a front-end load balancer, which balances load across multiple servers at the backend. So we found that the combination of ShaRE and Baker has provided us with significant improvement in programmer productivity. We could write all these applications in 10 days each. We picked a group of 3 graduate students who could write all these applications even without knowing Baker before. They could learn Baker and also write these applications. And this has also led us to have portable and reusable code. You can use the same code to derive other code. And we can make these applications also complex. The second goal of such a runtime system is to provide robustness to traffic fluctuations on the prototype. So we took a simple combination of services, each compiled into a single aggregate. There is a classifier that classifies incoming packets into either port scanning service or a SYN flood service. On the packets, you're providing one of those services, and each of them is a single aggregate. On an IXP 2400, there are 8 cores in total. So we have to use 4 cores for drivers and putting the classifier, etc. So we are left with 4 cores for adaptation on a single IXP 2400 chip. So these 4 cores are what we are using for adaptation for these 2 aggregates. The upper part of this graph shows the traffic fluctuation that we've created for each of those aggregates, and the bottom part shows the processor allocation. And you can see that if you just follow the green line here and the green line here, the processor allocation follows the traffic. So to summarize, I have talked to you about the Shangri-La runtime environment, which contains a packet processing oriented resource abstraction layer, which contains a scheduler that is agile and non-work conserving. This non-work conserving is actually counterintuitive. I forgot to tell about this point. Typically, schedulers are assumed to be work conserving. It's better to always choose a work conserving scheduler, and this was non-intuitive to have a non-work conserving scheduler in our system. And it has several adaptation mechanisms, all of which together simplify the programming of these high-performance network services on multi-core hardware and utilize hardware features provided in order to maximize the throughput of such services and make the system robust to traffic fluctuations. We believe that this kind of an environment will enable building high-performance virtualized routers which will address the internet ossification problem. So what I talked to you about in detail today is ShaRE for virtualized routers. The focus of ShaRE was simplifying application design and automating resource management. With the same research theme, I have in the past also worked on self-tuning wide array replication and efficient server clusters. I'll talk a little bit about the wide array replication and server clusters. Speculative replication of data and services has been shown to improve response time and availability of data to the users. However, the speculative replication can interfere with the demand traffic, the traffic on which users are currently waiting on. There have been techniques in order to restrict the amount of interference of such speculative data by using manual tuning, manually tuned thresholds. That means you restrict the amount of data that is transferred speculatively. However, these manual tuned thresholds can either be too conservative or too damaging because network conditions change with time. The capacity that is available at a server can change, and even at clients that's the case. What we ended up building in order to solve this problem is a self-tuning resource management solution which avoids interference at servers, networks, and clients and only utilizes spare capacity for such speculative replication. We built several mechanisms and also built a case study prefetching system in order to demonstrate that such mechanisms will allow us to address the interference problem and at the same time maximize the amount of spare capacity or maximize the utilization of the spare capacity at each of these resources. Earlier in my graduate school, I also worked on developing one problem that will help us build efficient server clusters. One of the problems in server clusters is that clients and servers use persistent connections in order to exchange multiple requests and responses. Now, this kind of using persistent connections amortizes the overhead of connection setup over multiple requests. Multiple requests can be addressed on a single connection. However, if the server side ends up being a cluster and there are different servers which are best suited for different requests on a single connection, then persistent connections will make it hard to redirect the request to the best server. And what we ended up building is a mechanism that will allow us to efficiently hand off this connection on the server side without the clients without the knowledge of the client, and let the service get serviced at the best suited server. Let the request serviced at the best suited server. And this will enable us to effectively utilize the server resources. So all these three works that I've been doing have the same focus of simplifying application design and automating resource management. From here, where I want to go is, first of all, I've learned different things in these different domains. One direction I would wish to pursue is to combine the techniques that we have developed in these different domains and build end-to-end network, usable end-to-end network services. For example, using the wide area application techniques and virtualized routers, I could build a high-performance speculative replication overlay, which will help us distribute speculative data efficiently and at the same time does not interfere with traffic. And similarly, I can build a wide area load balancer overlay using the virtualized routers and the efficient server clusters. In a different direction, I'm also interested in looking at these general purpose multi-core processors that are evolving. These processors contain similar features as the hardware that evolved for the virtualized routers, that multiple cores, multiple threads per core, and contain several hardware accelerators on the processors. Additionally, there are problems that come up with these dense multi-core processors. As the density of processors is increasing, the power consumed by these processors have to be controlled, because there is a peak budget that these processors have to meet. And that in itself becomes an important consideration in developing an operating system or a runtime system for such systems. So I would want to address such problems in the near future. So that brings to the end of the talk. I take questions. So I want to come to that question, why 2.1 milliseconds, right? Okay, sure. That's the slide. Now, when a packet triggers adaptation, I need to make sure I need to know that that packet is going to miss its delay bound. By the time it exits, that processor that I'm adding is ready to process this packet. That's when whatever I have added is beneficial. Right. There is a queue I'm monitoring, and on a packet arrival, I'm saying that this packet has made the queue length cross the threshold, and that's why I'm adding a processor. But it's possible that this queue will drain even before this processor comes up, because the packet processing rate is much faster than the context switch time. I derived a condition which will make sure that this packet will actually meet its delay bound. How do we do that? Let's say this is the point where I'm initiating a processor allocation. This is where the packet P arrived, and the queue length became queue length j plus 1. I have d units of time before I process this packet, right? This is time axis. Now, after t switch amount of time is when this processor comes up. So I can calculate the rate at which the queue is departing. The rate at which the queue is departing here is j, if j is the number of processors. J by t packet is the rate at which the queue is departing. And here it's j plus 1 by t packet. So if I write out a condition, what I have is that the number of packets that I'm processing in t switch amount of time with this rate, and in d minus t switch amount of time with this rate, should be that packet that came in, queue length j plus 1, right? So that makes me derive this relation d greater than t switch plus t packet. Right? T switch in our experiment was 2 milliseconds, and t packet was less than 100 milliseconds. So I chose a d value of 2.1 milliseconds to ensure that there is a design point which I'm picking. Okay. Any more questions? Yeah.
So if you have two aggregates that need to communicate with each other but get back to non-neighbors in your perspective, can you actually avoid using global memory by sort of routing things through the intermediate guy? Can the processing element act as routers?
Can the processing element act as routers? Yeah. Although we need Actually, we don't need even compiler support. We can do that at the using the runtime system itself. You just need to create that code which will act as the router. Each packet it is taking from the one next neighbor channel and putting it into the next neighbor channel. Yeah, you can do
Is
that.
this something that the programmer would have to decide?
No, he doesn't have to. That's what I'm saying. I can create a code that just acts as a router. The compiler can provide an aggregate, which is a router aggregate.
Right, but the question is whether to do that or to use a global memory.
Mm-hmm.
It's not always a clear decision, right? It would depend on exactly how much contention is there for the global memory and so on. So,
And how far apart these
right, and exactly how far, I mean, if you have to route 5 hops versus go once through the global memory. So the question is, I mean, does this happen automatically or is this something that...
So that's a policy that you can put into the ShaRE, into the runtime system. It doesn't have to be done by the programmer. All you need is one aggregate that does the routing functionality, and the ShaRE runtime system itself having the knowledge that at this point, my measurements show that it's better to use multiple routers and use this next neighbor channels as opposed to going through the global memory. There's a policy that is making this decision.
So the runtime system, for instance, will decide that let me not allocate any processors to this aggregate because I don't need this routing function at this time. Is that
Right.
It would do that.
Mm-hmm. Yeah. It doesn't do it now. I'm saying the mechanisms that we have done will provide that functionality. You have to write a policy which will provide that.
Do you have a priority policy so that, say I was trying to just forward packets, regular IP packets and maintain a sustained forwarding rate, but at the same time I have a lot of these processes, aggregates running on across the cores. Is there the idea of priority in the scheduling such that certain aggregates won't be removed from the cores?
Certain aggregates won't be removed. Okay.
Yeah, so say I have the IP forwarding. I want to guarantee a sustained forwarding rate.
Right. So that's where the overload control policy that I was showing comes in. There is a guaranteed allocation that you're providing to each aggregate. As long as there is traffic for that aggregate, if it's an IP forwarding aggregate, suppose, right? And I know that there is always going to be traffic for that, right? I'm saying that 10 processors will be allocated for that. That overload control policy will take care that 10 processors is always allocated to that, irrespective of how the load is fluctuating everywhere else. Because that's a guaranteed allocation you provide.